These pale, streaky, strung out lenses are granitic pegmatites, and they're sat within a shear zone. Lots of deformed rock around here. Well, I've come here to a place called Torrisdale on the north coast of Scotland to explore the relationships between pegmatites and deformation. It's a really intriguing story, and one that addresses something I call the pegmatite paradox. These types of relationships are commonly cited as evidence that the intrusion of granitic magma into the continental crust facilitates deformation by making it weaker. The premise relies on the idea that liquids, the granitic magma, are weaker than solid rocks. So intrusion weakens the deforming crust, or the shear zone within which the magma is intruded. But as a counterpoint, once the magma solidifies, we get granitic rocks rich in felspar that will be stronger than the surrounding country rocks. We'll be exploring these outcrops at Torrisdale to examine if pegmatites enhanced or inhibited deformation as they intruded and then solidified. So let's see the geology. So these outcrops at Torrisdale consist of some country rocks, which here are these sort of black materials, very dark. They're sort of amphibolites, bit of basic rocks. There are also some psamites and also pelites in here. So the area contains these rather spectacular pegmatite sheets. Let's look at the textures inside them. So some pretty coarse crystals of felspar in here, some quartz around the edges. So these are classic pegmatites, coarse-grained rocks, and they're preserving solid igneous textures here. So the main pegmatite bodies have also got these little stringers or wings. The fancy name's apophyse, that comes off the side, sort of injected into the country rocks from the main body. So that's a component in our story. Okay, what else can we find in these outcrops? Well, the pegmatites are folded, so they're deformed. They're involved in the deformation, or at least part of it. And the other part of the story is they're boudinaged, they're pulled apart. So how have the pegmatites deformed? We can look at a bit of detail now through these outcrops into really spectacular relationships to try and relate some of the folding, the little apophyses that have come off, the fold shapes in the pegmatites and their stringers, and particularly the boudinage. And then we're going to look at the internal structure of the pegmatites. What state are they in when all this deformation is going on? It's a bit of a paradox. Let's see if we can sort it out. So we can use structures like this to tell us about the relative competence or effective viscosity of materials at the time of deformation, in other words, how strong they were relative to one another. So here we've got a buckled layer which is making the buckle folds like this. It's more or less retaining thickness as you go around the fold structure. So that tells us that the single layer, this was more competent, stronger than the surrounding rocks at the time of the folding. It's a really useful criterion for actually checking or deducing the relative strength of rocks during deformation. The other criterion we can use is boudinage. I've cheated a bit and I've gone to look at some Lewisian outcrops here, so some much older gneisses with these amphibolites, and this amphibolite has been stretched up and down the cliff, and because it's broken and it makes the boudins, the sausages, it tells us that at the time of deformation, the time of stretching, the amphibolite, the black layer here, was stronger than the surrounding gneisses. It's the contrast in strength, or relative viscosity, that governs the structure. Relative strength is sometimes called competence. In these cartoons, the green layers are all more competent than the pink surroundings, but layer 1 is only slightly stronger, while layer 4 is much stronger than the pink. All layers stretch out, but the stronger layers break, or boudinage, into strings of sausage shapes. So, boudinaged layers are more competent than their surroundings at the time of stretching. Likewise for buckling, a phenomenon that requires strength contrast in rocks. Layers with little viscosity contrast, such as layer 1, just thicken up without folding. The greater the strength or viscosity contrast with their surroundings, simplistically, the shorter the fold wavelengths. Here, it's layer 5. And the final criterion, for buckled interfaces between different rocks, it's the weaker layer that pinches in, while the more competent layer is bulbous. Now let's apply these ideas to see if the pegmatite bodies deformed as weak objects or as strong, competent objects. This is a key question to answer for finding if they serve to weaken or strengthen the shear zone as a whole. So some pretty nice folded pegmatite through here. You can trace it around in here. Nice return hinge like this, and it goes up and over. Well, let's just look at the relationship between the pegmatite and the country rocks in here. There's a really nice fabric relationship, so let's get a closer look in here. So the pegmatite makes this really classic bulbous form, so a nice big broad round hinge around this side of the fold. In the core of the fold in here, I can see that the country rock comes in and makes these pinched in shapes like this, and the pegmatite makes these bulbous forms. And it tells us that the pegmatite was more competent than the surrounding country rock in here at the time of folding. So here is a rather thinner pegmatite layer, and it's folded into these rather spectacular buckle folds. So it's telling us that the pegmatite was more competent than the surrounding rocks at the time of deformation. From the folds then, we learn that the pegmatite bodies were stronger than their surroundings during deformation. Let's keep exploring. So here is another pegmatite, and you might see that it's folded so that we can trace it out like that. But as we follow it up the hill up in here, notice that it just boudinages out as we trace it sideways. Let's just change our view and look along it. So as we trace the pegmatite along, it comes along here, goes around a fold structure or fold pair like this, and as we trace it further up, it's been boudinaged out and stretched out. Boudinage. And again, the pegmatite deforms a stronger material than the rocks around it. And there's more. So get up a bit higher, and there's some really spectacular, clean outcrops blasted by this blown sand. Really great detail you can get out of them. So let's look at the relationship between this pegmatite body and the surrounding material. And I can see straight away that there's an apophyse, a stringer, coming off the side of the main pegmatite body and getting tracked off and almost getting lost into the mown foliation. But I can also see this foliation comes along like this and is truncated by the pegmatite. So clearly the foliation was there before the pegmatite came, and the foliation is folded. This is an example of flanking folds, and they tell us that this body, this pegmatite body, has spun during the deformation creating the fold. So let's just cartoon out how these flanking folds form due to shear and rotation of a rigid body. As the rigid inclusion rotates, it entrains some of the surrounding rocks, creating folds against the inclusion margins, and the folds betray the kinematics. So we can deduce from the flanking fold geometry that this pegmatite body has rotated like this. So in order to get that rotation, we have to spin it like that. That's a right lateral or dextral shear through the surrounding material. And it's the same shear sense we get for all these pegmatite bodies in these outcrops. Well, even on these little boudins of pegmatite, I can still spot flanking folds. So the fabric comes along here and then just at the very end tucks in and has a high angle against this side of the pod. And we can do the same on this side. It comes around in here and just abuts into this little corner here, slightly covered by some sand. So this pod has actually started off like this and spun in that sort of fashion, taking the fabric with it as it's gone. So really great evidence for right lateral shearing, spinning the pods around, creating the flanking folds. Great stuff. As the rigid inclusion rotates, it entrains some of the surrounding rocks, creating folds against the inclusion margins, and the folds betray the kinematics. So these outcrops show dismembered pegmatite bodies that have been pulled apart and rotated by deformation in a shear zone. But these bodies were once molten. So far, we've concluded that they behaved as strong objects, presumably therefore they weren't molten or weak at the time of deformation. But, to be clear, let's contrast weak and strong behaviours. In structural geology, isolated objects in a matrix are sometimes called inclusions, and we can contrast the behaviour of weak and strong inclusions. Weak inclusions behave like this. The surrounding fabrics pinch onto the inclusions and strain localises onto them too. And we just don't find these telltale structures at Torrisdale. So what about strong inclusion behaviour? These inclusions boudinage and show rigid rotations, evidenced by these fabric relationships. And it's these relationships that are found throughout the Torrisdale outcrops. So let's put some of this together and synthesize what we found, going through the various field relationships. So we've seen that the pegmatites are boudinaged as they're spun in this shear zone. The folding has the same kinematics as we might expect. The pegmatites behave competently, so they boudinage and they make buckle folds. Okay, so no great surprises there, because a coarse felspathic rock like this you'd expect to behave more competently than the surroundings. But that's only half the story. Let's look at the internal crystalline structure of these deformed pegmatite bodies. This is dramatic, isn't it? We've got a blob, rather like a loaf of bread, of pegmatite in here. Really nice example of a flanking fold behavior in here. So the fabric comes on, shows a high angle against the margin of the pegmatite in here. There's another one on this side, again, which confirms this general rotation of the boudin, of the pod, during the deformation. But look at the internal structure. So this is just a lump of moss, but look at the size of this felspar crystal in here. I can see there's interstitial quartz going around. So we've got a crystalline interlocking fabric of felspar with interstitial quartz between it. So really good interlocking crystals of felspar. This is an igneous texture, a primary crystallization texture with all the interstitial quartz filling in the residual porosity between the
main felspar crystals. And we're right up against the Boudin neck in here. So even in an area where we'd expect to see really high strain as the pod has been pulled apart, well, there's no deformation in the crystal fabric in here at all. This is an igneous texture. The pegmatite blob's clearly seen a lot of deformation in terms of its shape and how it's rotated, but internally it's undeformed, even at the Boudin necks. So if you just look at this, it looks like internally, it looks like it's post-kinematic crystallization. If you look at the shape, it tells you that it's pre-kinematic. So what might be going on here? Could it be both?
So, an array of Boudins. We can see the fabric bending or being squashed in at the Boudin necks in here, so it's all behaving as you might predict. So if this starts off as a 50 centimetre wide pegmatite, and then it's been Boudinaged, then these bodies have been thinned by probably a factor of 2, and in the necks, well, there's been a lot of flattening to change the shape and the thickness from here right down to there. So we'd expect to see an intense deformation fabric associated with the thinning of the pegmatite. So let's look in here. What do we actually see? Well, I can still see really good chunky felspar crystals, obviously in the middle in here, right down to the edge. In fact, there's quite a good array of big, large felspars in here, and if you look really closely, you can see that between them there's the interstitial quartz, and there's no fabric in the quartz either. So we've still got essentially an igneous texture regardless of where we are within this Boudin pod. So that's the pegmatite paradox. If you look at the internal structure, it suggests that the crystallization of the pegmatite happened after it achieved these shapes. The shapes are indicative of intense deformation, the folding and the boudinage. And what's more, the state of the pegmatites during that deformation, well, they behave more competently, stronger than the country rocks. How could that be if they were also molten?
Here's the paradox of apparently conflicting observations. They buckle and boudinage, but have igneous textures. The structures imply strong behaviour, but the textures suggest pre-solidification deformation. These seem to conflict with one another. Were the pegmatites solid, or were they molten?
So we have this conundrum, this paradox of strength, deformation and crystallization state. How can we resolve it? Well, we need to think a bit about pegmatites.
Granitic pegmatites, while being coarse-grained, are commonly zoned or layered, indicating that their solidification was pulsed. Coarse crystals can form rinds like this, so early in their solidification, the intrusions can become encased in a strong skin. But there's more. Granitic pegmatites solidify from hydrated melts that have exceptionally low viscosities, which means that they're pressed out by active deformation and can migrate a long way from their source regions. The presence of impurities like water, generally termed fluxes, keeps melts from crystallizing until they reach temperatures well below their normal freezing point or liquidus. But undercooled melts, once they start to go, grow big crystals very quickly. Felspars can grow centimeters in weeks. So an intrusion could have a swarm of crystals, which, if all solid, would deform and make plastic shape fabrics. But if the large crystals sit in residual melt, they can move but not really record deformation at all. They're moving as rigid bodies within the intrusion, so that once everything crystallizes, the pod has an igneous primary texture. But experiments also show crystals nucleate preferentially on intrusion walls, so they can form rinds on intrusion margins very rapidly. Crystals nucleating on intrusion edges are commonly seen, forming distinct textural zones in the pegmatites. So, in these cartoons, pegmatites can make lozenge-like bodies with strength, but retaining a liquid interior as they deform as strong inclusions. Cracks in the rind can blow out to give veins or apophyses, breaking out into the surroundings. So here's the idea, that the pegmatites begin to crystallize really quickly, and the crystal growth rates are super rapid, creating a framework of large feldspars that create a body that's more competent than the surrounding rock. So even though there's still melt within either the middle parts of these bodies or dispersed between large interlocking feldspar crystals, doesn't really matter because this behaves more competently than the surrounding rock, so boudinages or makes those buckle folds. Interstitial melt, residual melt, can then be squirted out into the surrounding country rocks, making these apophyses, some of which are squirted out early so they see the rotation and are folded into the flanking folds, and others that cross-cut the flanking folds because they're squirted and ejected rather late in that rotation deformation history. So some people dismiss the geometries that we see here as due to a dike or a sheet of magma that has been drained, and the residual magma is left rather like peas in a pod. I think that doesn't do justice to the deformation that we see here. We've established that the boudinage, the podding of this rock, is associated with rotational deformation that we've tracked with the flanking folds. There's one there. So this isn't just a passive sort of draining of a sheet. The pegmatite is being actively deformed as it's boudinaging and breaking up, like creating these lenses. And yes, the melt is redistributed, or the residual melt in these pods is being redistributed as it happens, as the deformation progresses. But just saying these are collapsed sheets is just not doing justice to the full story. Great rocks. We can move on to look again at the folds. To recap, we saw earlier that this pegmatite layer has folded so that it deformed as a more competent, stronger layer than the material around it. So let's look a little more closely at the internal structure of this deformed pegmatite, at least deformed in shape. So I can see the long axes of the crystals of the feldspar growing off the side wall of the vein of pegmatite, a concentration of quartz in the middle, a little bit of interstitial quartz between the feldspar laths in here. So we have essentially a rind of feldspar on both sides of the veinlet, and then some quartz in the middle. It's a motif that we see elsewhere in the vein. The hinge area still contains proper igneous crystals of feldspar, basically unmodified. We can see in here that the crystal form is really simple, and there's quartz growing between the laths of feldspar. So the internal structure of this preserves a primary crystallization texture. So this material doesn't have the requisite deformation at a crystal scale that you'd predict from the shape of the body. If you just look at the grains, you would say that that is crystallized from a melt directly and hasn't really been modified much since. So perhaps these deformed when they were not fully crystallized. So melt arrives as a sheet in country rocks and then quickly grows a felspathic rind, and this creates a rheology prone to buckling. The rinds can shear past each other, decoupled on the residual melt interior, and then later freezing. Essentially, the residual melt was encased in a rind of crystallized felspathic coarse-grained material, essentially rather like a lozenge. So we can return to that rather nice fold structure we looked at earlier, and we can see that this pegmatite also is zoned. There's a felspar-rich zone on this side and on this side of the body, and the middle part of the sheet through here is, well, there's more quartz in it. I won't call it quartz rich, but there's more quartz, and you can see that it grows, or it's crystallized between these felspar laths through here, filling in the residual porosity between the crystals. So we can perhaps suggest that this body started off with very rapid crystallization of the margins, like this, but with an internal zone that had a significant melt fraction still within it. As the foldings progressed, maybe a lot of this melt has been expelled and forms apophyses elsewhere, but the residual melt that comes into here just crystallizes out at the end and just locks everything together after the foldings are complete. So the idea is that this body folded as a crystal mush, and these crystals are really large, so the body as a whole had a high strength compared to the surrounding country rocks, behaved more competently. But the crystals could sort of shake together and lock and reform, but we have an igneous texture essentially within here, and the residual melt just crystallizes quartz rich and fills it all in. And that's the pegmatite paradox. Deformed bodies with shapes that imply high competence, therefore solid, but interiors that show limited, if any, deformation, implying crystallization after deformation. The pods deformed while still molten. The paradox is resolved if these pods deformed while partly crystallized. A framework of large felspar gives strength, maybe dispersed, or as stiff rinds that grow rapidly on arrival of the melt, so that straight away the body behaves competently. The pegmatites deformed exclusively as objects that were stronger than their surroundings. Their addition, therefore, added stronger material to the shear zone. So, although they are deformed, they've not weakened the shear zone, they've inhibited deformation, though not stopped it entirely. So they're examples of deformation of fully crystallized pegmatites. This deformation's acted on the original preferred orientation of felspars growing in rinds. And we see an example here where the original felspars are still there, forming elongate forms, squeezed together as the surrounding quartz has deformed.
So the field relationships here all show that the pegmatites behaved more competently than the surrounding country rocks during deformation. Therefore, they strengthened the crust. They might have had a chance of weakening the crust at a time when they were fully molten, but that was such a fleeting period of time because they started crystallizing straight away. So almost on arrival, they add competence to our crust, even when not yet fully crystallized, simply because they grow big felspars. So pegmatites like this are actually not evidence for magmatic weakening of the continental crust. Quite the opposite.
Finally, we can graph schematically this behaviour up, plotting the strength of intrusions relative to country rocks, evolving over time. This domain is where intrusions weaken the crust. Classically, if granitic magma intrudes at this time, the deforming crust is weakened until freezing has crystallised sufficient felspar, after which further freezing strengthens the crust. Significant deformation could have occurred in this protracted weak state, because crystallization is slow. But pegmatites are different. They arrive, and because they're undercooled, begin to crystallize almost straight away, growing large felspars. Even a body with some residual melt is stronger than its surroundings, so pegmatites strengthen the crust. There's just not enough time to accommodate significant strain while fully molten.
Granitic pegmatites strengthen the continental crust. Well, you can find out more about the pegmatite paradox and these outcrops in a paper that I've written up with Taya Torvella a few years ago now. Describes these outcrop relationships and their importance for deducing rheology of deforming crust. But otherwise, why not visit the outcrops themselves? It's a wonderful location.